Okay, so we're going to go over section 7.2. We introduced last chapter some stuff about work with springs. You remember that? Yeah. And something called Hooke's Law. I'm going to review that because it all comes back up again, but we're going to take a little further and talk about the energy aspect of it as another form of potential energy. So last 2 days, we've been looking at conservation of energy and kinetic energy and potential energy and possibly work other involved with it. The potential kind, though, we've talked about the last 2 days, has only been potential due to gravity. So like lifting something up, it has the potential to fall, right? But there's other forms of potential, or also known as stored energy. And another one we come across a lot in mechanical physics is elastic potential energy. So that means overall, elastic means anything that you could stretch or compress that goes back to its original position. But most of the time, when we're talking about elastic potential energy, it's springs, because they commonly do that. But this would even go for like rubber bands and stuff like that. That would kind of follow the same idea. But anyways, we're going to focus on springs. So we did introduce this last chapter in one section, but I'll just go over it again. Hooke's Law. It's a simple formula that gives you the magnitude of the force needed to stretch or compress, actually, either way. Some springs could compress and stretch. Some could only stretch, possibly. But it's the force needed to do either one of those. We discussed last chapter that K is called the spring constant. It was like the value that basically is like how strong is a spring. It's in newtons per meter is the unit we learned. And basically, the strength of the spring is affected by a handful of factors, like what is the material it's made out of, how large are the coils, things like that. Okay, but that's essentially like the higher values for K means it would be really hard to stretch or compress it. Lower values would be pretty easy to stretch and compress it. If you were, just to like throw it out there, if you took like the springs that are used in suspensions of vehicles, they have really high spring constants. They're really hard to compress because if they compressed easily, then it wouldn't really be useful in order to absorb the energy from like a pothole or something like that, or running over something. And then X is just the distance stretched or compressed, which we typically want in meters if it's not already. So that's what Hooke's Law is. And if hopefully, if we're ever back to somewhat normal, we do have a lab that kind of hands-on with springs that we'll learn a little bit more about that with. So another thing last chapter, after learning about Hooke's Law and how to find the force necessary, is how to find the work done by a spring or on a spring. All right? Just keep remembering, I know I keep saying this, but when we have positive or negative work and or positive or negative energy, work and energy are scalars, so positive and negative. Like positive means energy put into the system, negative means energy taken out of the system. So basically that means there's two ways to look at the formulas for work in springs. If we want the work done on a spring, by literally like the force grabbing it. So I'm going to flip over to my simulation you saw once before in the past. So I can move this rod that's attached to the spring. This rod that I'm pulling on with this little hand is stretching and compressing the spring, right? So if I use this version, if I use this version of the formula, it's the work done on a spring by what's doing it, by what's that rod's pulling on it, and I'm pulling on the rod, right? And it's just 1/2 K, the spring constant, times X, the distance stretched or compressed 2 squared, minus 1/2 K X1 squared. And X2 and X1s are just a later position minus an earlier position, like a final minus initial, okay? So in that order, that finds the work done on a spring. If we flip-flop the order of this, that's the work done by the spring. Because as I noted last chapter with stuff like this has a equal and opposite thing to it like Newton's third law has. Because when I pull to the right on the spring, which way does the spring want to pull back on me? To the left. Or if I push to compress it to the left, it wants to push back to the right on me. That's why there's like two different ways to look at it. But the amount for the same situation, if you use these same two formulas, the overall amount of work would be the same. Just one of them is going to be positive, one of them is going to be negative. Okay? And where the equation for elastic potential energy, remember U means potential energy in general is a symbol we usually use. It kind of comes then from the same idea as where we derived the potential energy due to gravity one. We showed last section, the last 2 days, that how we figured out what potential energy due to gravity was coming from its work equation. Because work and energy are practically the same thing. All right? So it comes from the same place over here. So the most important thing is probably in this chapter that potential energy, elastic potential energy, stretching or compressing things like springs, is just 1/2 kx squared. That piece of these formulas is the potential energy. Now that we know that, we could mix these equations together, which is all this is, if necessary. But to be honest with you, I don't have that box because it's not always that necessary. As long as you get the gist of all this, that's what's important. We can now put this into conservation. All right? Remember, if there's no outside forces in a system that's like friction or significant air resistance or anything like that, then we can still use the law of conservation of energy with potential and kinetic. And we could have multiple forms of potential. So yesterday's and last 2 days stuff was like the kinetic plus gravitational potential at some initial scenario should equal the same amount later, right? That's what conservation means. The before should equal the after. It just might be divvied up differently, right? So same thing applies here. We might have situations where we don't have gravitational potential, but we have elastic. That would again be like something like this system. All right? It's horizontal. It's not vertical. So we only have, if I released it, and this simulation doesn't let me release it, so we'll just have to imagine it. So if I pull and stretch this and then release it, and it goes back somewhere back here into motion, then that would be a perfect scenario where I could use this form of law of conservation of energy with kinetic and elastic potential, and then break down as needed and putting it in those same sub-equations. But if necessary, I could write a really big conservation of energy equation that maybe we have a vertical setup with a spring. And if we have a vertical setup, then there's the possibility that gravitational potential energy is involved, right? Because maybe we have something and we're going to have a problem like this that falls on a spring or something like that. And we could include work other if there is like significant friction. Or another thing work other could be was like pushes or pulls to the system externally, not just letting it go, right? So same thing as yesterday. So we're just could have uglier situations where we need all of that, and we could just put it all into that same idea of conservation. So that's all the new stuff. So now we're going to just go through a few examples before we assign the next set. So example 7.7 is on page 215. And again, since the book has a pretty good diagram, I didn't draw one here. But it is similar, not the same, but is a similar setup to maybe something like this. It's just that a mass is attached to the spring, and it can push the mass and make it possibly go back and forth. That's the kind of setup we got here. All right. So, but since it's setting on a surface, no gravitational potential will be involved in this problem. It'll all be due to elastic. So it says a glider with mass of 0.2 kilograms sits on a frictionless horizontal air track. So we don't got to worry about work other because of friction. It's connected to a spring with a force constant K of 5 newtons per meter. If a problem never gives you what K is and it seems like you need it, look out. They probably give you the force and the distance stretched or compressed where you could use Hooke's law to find it if needed. But this one straight up gave us K. You pull on the glider, stretching the spring 0.1 meters, and release it from rest. So to kind of show, again, this simulation doesn't release it, but you pull on it and stretch that spring that the block's connected to, and then let it go, and then the spring will try to pull it back in the other direction, right? So it's important to be able to visualize what's going on in this. The glider moves back towards its equilibrium position, and its equilibrium position is the x value, the x in all these equations. That's where its natural rest position. So if you stretch the spring or compressed it, then let it go, it eventually settles down to its natural rest position. That's where we would call the equilibrium position, x equals 0. So it goes back towards that. That means it's going opposite of where you pulled it. What is the x velocity, horizontal velocity, when x equals 0.08 meters? So we stretched it 0.1 meters, and it's now going back towards equilibrium, and as it's going back, it's being pulled and it's in motion. But if it's still being pulled or pushed by the spring, we still have at that moment elastic potential, and since it's moving, we have what other kind? Kinetic, exactly. All right, so, and since there's nothing else, there's no gravitational potential, and there's no work other involved in this situation, it's all being done by the spring's energy, the work, we could just use the most basic form of the law of conservation of energy, that the kinetic plus elastic potential at the beginning equals the same amount, total amount somewhere later in time at position 2. So we list all our givens. The mass of this block that was against it is 0.2. K was 5. X at position 1 is 0.1. And it was released from rest, therefore Vx1, horizontal velocity 1, is 0. We're being asked about position 2, which is given as 0.08 meters. And we want to find the horizontal velocity as it passes through position 2. So that's our unknown. So, again, just to stress values, I kind of figured out all these pieces separately, but you could do it all at once in the equation when you're solving them if you want. So, since we released from rest, there's no initial kinetic energy, right? K1, 0. Potential 1 right here is 1/2 times the spring constant 5 that was given times position x1, which was 0.1 squared. So that means, to begin with, all our energy is in this form, right? Which is 0.025 joules of energy. That means anywhere later in time, since that is the total because there was no kinetic, anywhere later in time, all energies have to add up to that. All right, since that's the total before. If it doesn't, that must mean there must have been work other involved or I made a mistake. Okay, so the right side of the equation, since the spring is still pulling through the 0.08 position too, it still has some potential, elastic, and it's moving through it, so there's both of those exist in position 2. Neither one of them 0. So if I solve this equation for K2, and the reason why I want to is because my goal is to solve for V. V2. V2 is within the formula for K2, right? So I solve for K2 by subtracting U1 over, and then I could plug in the formula 1F mv2 squared, plug in my other values. I separately found the potential at position 2 over here elastically, which was the 0.08 position. Ran that and got 0.016. Pop that in there, and then I just isolate for V. Multiply by 2, divide by m, and square root it, and I get a V2 horizontally of negative 0.3. I should put the units on there. That would be meters per second. Okay? Now, when I solved for V, I had to take a square root, right? So, it specifically said find the x velocity. If it says find the x speed, then I don't even have to put a sign on it, because speed's a scalar, right? But it did say find the horizontal x velocity, and since I had to solve by taking a square root, my answer could be plus or minus, right? So we gotta again pick what makes sense. Remember, this system was initially stretched to the right, and most of the time we'll probably call right positive, right? So if that's the case, the spring's pulling it back to the left, which is why I threw a negative on there. That makes sense? Any questions on that one? That's a pretty, as long as you know the equations, a pretty basic one. So let's now move on to example 7.8. Basically one where we do have work other involved. Similar setup, but we're going to have friction involved. It says, suppose that same glider we were dealing with in example 7.7 is initially at rest at x equals 0. So it starts at the equilibrium position with the spring unstretched. You then push the glider with a constant force that has a magnitude of 0.61 newtons in the positive x direction. What is the glider's velocity when it has moved to x equals 0.1? So this is actually going back kind of like a prequel to the last problem, okay? The last problem started that we had already had this spring at 0.1 meters. But now something had to eventually get it to 0.1 meters, right? By either stretching or compressing it. In 7.8 it says you are stretching it by pushing on it with the force of 0.61 meters. So during this process, you're applying a work other on it, right? Your force is considered a work other because it wouldn't magically stretch itself, right? All right, so with that in mind, we need to find the velocity when it has moved to 0.1 meters. So I'm still pulling it. I may even be pulling it through that position. But the main point right now to start is it was settled down at equilibrium and just sitting there, right? So it had no kinetic energy to start initially, K1. Agreed? Elastically, if the spring was just sitting there, nothing touching it, it has no elastic potential energy, right? Therefore, the only way for this spring to gain any kind of elastic potential energy is for a work other to either pull on it or push on it, right? And that's exactly what's going on here. So all the energy to begin with is in the form of being done by work other from the pull that it did. Remember, work is equal to force times displacement, right? Going back to last chapter. So it gave us the force. The force is 0.61 newtons we put on it, right? And we stretch it 0.1 meters, right? We want to find the velocity as I'm stretching it through 0.1 meters. I'm not stopping at 0.1 as I stretch it through if this force remains at that amount that I stretch it with. So the whole left side of our equation is work other, which we found right there separately. So it'll equal K2 plus UE2 at the 0.1 position. So at the 0.1 position, U elastic 2 is 0.025. I plug in the formula for K because I need to solve for V. I rearrange it and find that the V is 0.6 meters. And it is positive because if I'm stretching it to the right, and I define that as the positive direction, I'm pulling it through that position, right? So if I maintain this force of 0.61 newtons that I used up here in calculation that was given, and continue to stretch with that force, that's how fast it'll be going as I go through that 0.1 position. Does that make sense? Okay. And I think this is the last example. One more example. This is the one that includes, it has the most going on. It includes, it's a vertical situation. There's a lot going on. There's friction. There's also potential energy due to gravity of an elevator, it looks like, that fell. So flip over to page 216 if you're not already there, and look at example 7.9. And for the third time, there's again a really good diagram in the book you should be looking at while we explain this of the system going on. It says we got a 2,000 kilogram elevator, which for whatever reason they already converted it to newtons for you, but you could have done that on your own easily. With broken cable and a test rig is falling at 4 meters per second. When it contacts a cushioning spring at the bottom of the shaft, the spring is intended to stop the elevator compressing 2 meters as it does so. Compresses point to stop the elevator, and it compresses 2 meters as it does so. During the motion, a safety clamp applies a constant 17,000 Newton frictional force to the elevator. Why is the necessary force constant? What is the necessary force constant K for the spring? Overall, this is really a real world engineering situation when you think about it. There are multiple safety features for elevators. It is extremely rare in the last few decades, probably, for there to be any kind of major issues, especially with fatalities on any kind of modern elevators. Because there's usually a kind of triple system in place to protect you. Number one, there's not just one cable. All right? If there was only one cable and it snapped, you'd fall, right? But usually there's multiple ones. All right, so if one fails or gets stretched or something too much, you're still good and it would never fall in the first place. But there's also worst case scenarios. Let's say something happens and all the cables break. If there was nothing else there and you were in a high floor, you're going to just come crashing down, right? Or if they break or are released somehow from their winding system or whatever. So the next thing in place is almost like a braking system. It's a mechanical system that it's basically on rails. And if it starts to move or drop too quickly, mechanically, basically, frictional brakes are pretty much applied. They refer to them as, a safety clamp in this problem, all right? And that would drastically slow you down. But just in case, there's often another third thing that's a cushioning effect at the very bottom of the shaft of the elevator. That's basically a platform with a spring on it that would cushion you if it even got that far to you hitting it. And that's the spring we're talking about to have what force constant was needed. Because if you're developing something like this, you don't just manufacture a spring and say, well, I think this is going to work. If all else fails, it's got to be a spring that's, if it's too strong, if it has too high of a spring constant, it's still going to be like hitting a brick wall, okay, or a concrete floor. But obviously, if it's too low of a spring constant, the energy from the fall when it hits it could just completely collapse it like it's not even there, and you would still hit very hard. It has to be a spring with the constant that is able to absorb the amount of calculated energy that could possibly happen if everything else fails. So that's the situation we're finding here. All right. So it does tell me the cables are broken, and it's falling at 4 meters per second when it comes into contact with the springs at the bottom of the shaft. So the moment it touches the springs, notice it has point 1 and point 2 in their diagram, right? So position 1 we're going to use because they already identify where position 1 should be. You see that? Point 1 is the moment it contacts it. And at that moment is the 4 meters per second when it contacts it. So at that position, because it gives us that as point 1, is going to be the equilibrium position of the scenario. All right? So let's start breaking down a few things. Okay, I have all the givens here. It will eventually come to a stop if everything works right? So V2 I set at 0. So the initial kinetic energy at the moment of contact of the spring, we could find by using the given mass, 2,000 kilograms, multiplied by the 4 meters per second. So due to kinetic energy, at that moment of contact, it has 16,000 joules. K2 is 0 because it comes to a stop, right? Or we want it to come to a stop. Now here's where we got to be careful on this one. And we basically did it this way. There could have been different ways to look at it where you set equilibrium position. However, it kind of guided us to this by giving us a diagram where they're telling us point 1, position 1, and position 2 is. All right. So position 1, we're going to make the 0 position, like I said earlier, as far as measuring everything too. And by everything, I mean for elastic potential energy, that's going to be the equilibrium position where the spring, if we just contacted it, it hasn't compressed it yet, right? So the spring isn't stretched or compressed. But if we make that the initial position of 0 for elastic potential, we also should make that the reference level position for the gravitational potential, because this thing is falling into it, right? It's falling a distance of 2 meters from point 1 to point 2. We can see in the diagram, right? So since we're doing this, since right here above is the reference position for all those kind of measurement values for distance, or displacement, I should say, I end up lower than the reference in the end, right? And if I end up lower, that means the y2 position, the y's are involved in my gravitational potential energy formula. U equals mgy, right? From yesterday, or the last couple of days. But if I end up beneath it, I'm actually at a position of -2. If I said +2, that would mean I ended up above it, right? So we just got to be really clear with that, just so we have all those values meshing to make the same sense of what's going on directional wise. All right. So that actually means if I set the reference level as 0 for y1, that there's actually no gravitational potential energy defined in this way to look at it at position 1. Does that make sense? Since we made y1 0. You're allowed to make the reference level anywhere you want for gravitational potential energy, as long as you measure everything from there. That make sense? Okay. So that means UG1's 0, but since position y2 is underneath the reference level, and we said -2 represents that, we actually get out a negative amount of gravitational potential, which is okay. It might seem weird, but it's okay. It meshes with all our values. All right? We all on board with that? Okay. And then finally, the elastic stuff. And again, I found it all separately. If you want to find it all within the equation, that's fine, but sometimes it might seem overwhelming doing it that way, but whatever. If you want to plug it all in together at once, that's okay too. But again, since the one position was the reference level, the spring is not compressed yet from there, so elastic 1's 0 as well, right? And elastic 2, we've hit the spring, it's pushed it down, and it pushed it down to -2. And because of the y position getting squared in this formula, the negative goes away. And our goal, if you recall, when we read it, is to find the spring constant necessary that this all works out this way, right? So we could just get an expression here. If I reduce the expression as much as possible, it comes down to 2k. And when I plug it into the entire conservation law, then I'll be able to solve for k. But don't forget about the friction as well. As we go from position 1 to point 1 to point 2, friction, those clamps are working, right? And we were told that the force of the clamps were 17,000 newtons, and it goes 2 meters during that. And friction always does negative work, all right? Because it always takes work out of the system. So somewhere we got to account for that and make sure we make work out there for friction negative, okay? So 17,000 times the displacement of 2 meters, because work equals force times displacement, again from last chapter, gives us negative 34,000 joules of work other that friction is doing. So we got a lot going on, but we got it all figured out other than K, what we need to solve. So we go to the biggest version of the conservation law, which includes all these energies and works, right? So putting in everything for position 1, actually a lot of it cancels out because a lot of these were 0, right? Above we defined UG1 as 0 and UE1 as 0, mainly because of where the reference level was provided at 0 right there. And we come to a stop, so K2 was 0. So really we just have these 4 pieces that are non-zero from above. Our goal is to find that K value which was involved in UE2. So eventually I'll plug in 2K from UE2 that I found above, solve for K, rearrange, and just run the math correctly, and we get a K value of 10,600 newtons per meter. If we have a spring with that spring constant, then this will all happen safely. In the worst case scenario of everything out, like cables failing. A lot going on, but if you break it down piece by piece, it's not really too bad. Any questions on that one? Okay, so I'm going to, for those of you at home, I'm going to post this video right now. And I'm going to post the new problems right now out of this section. They're on Classroom, or they will be in 1 second here. There's a handful of them. And you could use the rest of the time today to continue the problems.